Hello, everybody. It is a pleasure to welcome Dr. Daniel Bezdány, a distinguished mathematician at the Molay Institute of the University of Szeged in Hungary. His research centers on probability theory and stochastic processes, with a particular emphasis on the asymptotic behavior of a critical multi-type Galton Watson process with immigration. For instance, in a recent study, he demonstrates that under suitable moment conditions, scaled random step processes derived from a three-type Galton-Watson model converge weakly to a limit involving independent squared Bessel processes and iterated integral processes. Through his work, Dr. Bezdány has made significant contributions to mathematical modeling and analysis, collaborating actively with colleagues in both theoretical and applied mathematics. Based in Szeged, Hungary, he continues to advance our understanding of complex stochastic systems. Please join me in welcoming Daniel Bezdány, and please, you can start.
Thank you very much for the welcome. Although I would like to just correct a little bit. I'm only a PhD student, so I'm not a doctor, but thank you. Thank you also for the opportunity to speak here. I'm going to be talking about, as you heard, multi-type Galton Watson processes with immigration, specifically critical ones, specifically decomposable ones. Although I will start with a sort of overall introduction to this class of processes. This is based on joint work with Mátyás Barczy, my PhD advisor, and was supported by this particular project there. Okay, wait. All right. So I'll start with the introduction of this model that I'm going to be dealing with, the multi-type Galton Watson process with immigration. Then I'll introduce some classifications of these types of models and also recall some existing convergence results, which closely relate to our results here, or are very similar results. And then next I'll introduce the main results of this work, and then afterwards some rough sketches of the proofs and some of the ingredients, and also have some extra afterwards if I don't fill out the whole time of the presentation. We'll see. Maybe some related results I can show as well. So start with very simply just the single type, the classical Galton Watson process. We have every generation we have some number of individuals. So here from 1 through the x, k minus 1. In the k minus 1th generation, this is how many people there are in our population. Each of them independently produce some number of offsprings. And there are also some random number of immigrants coming into the population. And this makes up the next population number. Specifically, we can define this with this recurrence, this formula. So the next generation will be made up of the offspring of the previous generation's individuals and the immigrants as well. We're going to start this process from 0, but this is mostly for simplicity. If this process is not started from 0, then this is actually in distribution, this would be equal to the sum of the process starting from 0 and a process without immigration. But we're mostly interested in the influence of the immigration here, so we're just going to start from 0. And here, all of these variables, these offspring variables, and these immigrant variables or immigration variables are all independent, and the offsprings are identically distributed, and the immigrants are also identically distributed.
No independence in the immigration, right?
The immigration is also independent from the offspring and also from the x's. Everything. These epsilons are independent from everything else here. Can you see my mouse, by the way?
Yes.
Sure. Yes.
Okay. And the psi k are independent of all the past from 1 to k minus 1?
Yes, that's right. So every psi is independent from every other psi and from every epsilon as well.
Okay.
Okay, so this was the single type case. The multi-type case is sort of a straightforward generalization. So here we have multiple types of individuals in a population. We keep count of each of them separately, and each of these types can have different ways that they reproduce. So for the simplicity, let's say P is equal to 2, so we have two types of individuals. The first type can reproduce according to a particular probability measure, and the second type can reproduce according to a different probability measure. But here, once again, every psi and every epsilon is independent from everything else. So we still keep independence, and we also keep these offspring variables identically distributed, but now we split them up according to types. So all individuals of a particular type reproduce with the same probability measure. And just to not have to write so many indices, I'm going to introduce these variables. These are just used to represent the probability measures of either the immigration or the offsprings. Wait, sorry, not these.
Sorry, the size of the vector xk, capital Xk, it
Yes.
depends on k, depends on time, on generation.
So this is always a vector with p coordinates.
Okay.
So we have p number of types.
Okay, and all the components are independent. K1, xk2, xk.
No, the x's don't have to be independent at all. Actually, it turns out that in general they will not be, but and for the size, these are also not necessarily independent. So there can be some dependence relation between the offspring distributions of a particular individual.
Okay.
Also for the immigration, this is also true. So the coordinates don't need to be independent of these vectors, but different vectors are independent from each other.
And it is not possible to see the immigration as a kind of zero components of your psi?
I suppose it's possible. I think that would complicate the way to write this relation here, because how many xi's we add together depend on the size of the population, but the immigrants, we assume that they don't depend on the size of the population. They're always the same random. Immigration is always happens according to the same distribution.
Okay. You will have a picture of a tree after or not?
No, I just have this tree here. I thought the multi-type one would be a bit too complicated. I didn't think it would help much with understanding the
Okay, because I was not sure of what was the evolution of the individuals which were immigrants. If we see them as a tree,
I see. Yes, the immigrants can also be seen as just a tree that are separate from the, let's say, the original ones, but we're not going to really get into the lineage here. We're just going to be looking at the size of these variables.
Okay, thanks.
Okay, so this is the model we're going to be working with. There are several ways we can classify this. The first one, first of all, I'm going to introduce these representative variables. These are just they just have much fewer indices here, so I can write them more concisely, but they represent the immigration distribution and the offspring distribution of type I, in the case of psi I. So type 1 individuals generate offspring just like psi 1 is distributed. Okay, and then for calculations and also describing the classification, we're going to need these quantities. This A matrix is made up, so its columns are going to be the expected values of these representative variables. So the first column is the expected value of an offspring vector for an individual of type 1 would produce. Second column would be according to the offspring distribution of a type 2 individual, and so on. And B is just going to be the expected value of the immigration. And it turns out that A is going to be very central in describing the way our process behaves. But also I will introduce these VI values. Well, these are particular values of the covariance matrix of CI. In general, you can define it for the whole, but I only wanted to introduce these because these are going to be enough to actually describe our results. So this is just the variance of the number of same type individuals that an individual can produce for each I. So V1 is the variance of the type 1 individuals that the type 1 offspring that the type 1 individual can produce. Okay, A is the offspring mean matrix and B is the immigration mean vector. Okay, and with these one can show that this relation holds. So the conditional expectation of a particular xk is just A times the previous population size plus B. And then because we started the entire process from 0, we can use induction to get this relation. So the expected value of our process at time k is going to be this sum here, which is, as you can see, this is a geometric-like sum. It turns out, of course, that how this sum behaves relates strongly to the spectral radius of the matrix A. B here is just a constant multiplier for this sum. So that is what the first way that we're going to classify a process is by. So this is in line with the single type case. In the single type case, it's well known that you have critical, subcritical, and supracritical cases depending on the expected value of the offspring distribution. Here we need to consider the spectral radius of this offspring mean matrix, but it behaves similarly. So we have a subcritical case if the spectral radius is strictly less than 1, critical if it's equal, and supracritical if it's larger than 1. But we're only going to deal with the critical case here. The others are actually, so they usually behave very differently. And in the single type case, Corvée and Winitsky have this well-known result from 1989. This is the functional limit theorem for a single type critical Galton Watson process with second order moment conditions on the offspring distribution and the immigration distribution. Here, so you can see that the correct normalization in this case is 1 over n, and the limit process is a squared Bessel process. This can be described in several ways. We are going to use this source differential equation to denote this. So the solution to this differential equation is a squared Bessel process. This W is a Wiener process here. Okay, so I didn't use the notation that I previously introduced here, but here you can see that the expected value of epsilon here would be our B in the single type case, and this variance of psi here would be the V1 that I wrote in the previous slide. So if I use this, then it is B, and this is V1 would be here. Okay, so this is the type of results we're interested in, but in the multi-type case instead of the single type one. And it turns out that in the multi-type case, it's not enough to know whether the process is subcritical, is critical or not. We also need to consider the reducibility of the matrix, of the mean matrix. Okay, so recall that the matrix A is reducible if we can permute it so that it is block diagonal. So it looks like this. I chose to write this as a lower block triangular. Excuse me. It can be phrased as the other way around as well. So this is going to be a central idea for us as well in the multi-type case. And we call one of our processes decomposable if its mean matrix, offspring mean matrix is reducible, and indecomposable if the offspring mean matrix is irreducible. So it can be permuted to be block triangular. Particularly, we call it primitive if A is primitive, which is just irreducible, but specifically also aperiodic. So it doesn't have a period of one. And it turns out that so in the indecomposable case and the primitive case, functional limit theorems are already known. Ispány and Pap in 2014 showed result for the critical primitive case, and then Danko and Pap showed in 2016 for the general critical indecomposable case, functional limit theorem. I have some slides about these after the talk. I can show them if someone's interested. Just let me know. But we're going to be so because of this, we're going to be focusing on the decomposable case because that's not already known. For us, we're going to be an important note to make is that if a matrix is reducible, then actually we can always reduce it in a particular way so that it looks like this. So this is also block triangular, but specifically the blocks in the diagonal are all irreducible. So we can't make this more block triangular. Okay, so I'm going to use this capital N always for the number of block triangular, irreducible blocks in this triangular writing of permutation of the matrix A. This is the only equation I'm going to refer back to, so I'm going to name this star symbol. Okay, here these other matrices have some appropriate sizes. It's not going to be too important for us. They're competitive. They are as big as they need to be. And in this writing, we can so Foster and I have a result from 1978. This is about a critical decomposable Galton Watson process with immigration, where the matrix has that particular form what I showed earlier. So this form, where the diagonal is filled with irreducible matrices. And each of those matrices, so each of these matrices has a spectral radius 1. This doesn't actually need to be the case in general, of course. So for the spectral radius of the whole matrix to be 1, some of these can have spectral radii a lot smaller than 1. But if they are all 1, this is sometimes called the stronger critical case. So not just critical, but stronger critical. This is meaningful in the case of decomposable processes. And also the lower of diagonal elements. So these ones, these matrices are not 0, so they have at least one positive component entry. Then they show that this convergence holds. This is not functional, but they show that if you look at the first coordinates corresponding to the first irreducible matrix in the diagonal, then you normalize them by 1/n, and then you look at each sets of coordinates corresponding to the irreducible matrices in the diagonal and normalize them by larger and larger powers of n, then you have this convergence to a particular process. They also describe this process with its Laplace transform, but it would be very long to describe here. So I'll just say that this random variable x exists. If you would like to do something similar for functional limits as well. So in this in the 3-type case, we're going to consider this particular setup. So this is the A is not only block triangular in our case, but actually triangular, properly triangular. And also we look at the stronger critical case. So well, each matrix in the diagonal, in this case, each entry has a spectral radius of 1. So in our case, they're all equal to 1. And with this matrix, we can get functional limit theorems in 4 separate cases. So depending on the values of these entries of the matrix. Okay, so sometimes these can be 0, and sometimes they're positive. And depending on this particular number of them and which of them are positive or 0, the limit behaves differently. We're going to see that some of these resemble the single type case, but some of these behave differently. Okay, so I'm going to go through 4 slides here, which deal with each of these 4 cases. So the first one is going to be the matrix is just the identity matrix, and the second is going to be where there's some extra communication between types here, but we'll see how that influences behavior now. Okay, so first, this is the case where the matrix is just the identity matrix. In this case, each coordinate behaves like a single type process. So you can see here, these are all these W's are all independent from each other. They're standard linear processes. And these X, T1, X2, X2, 3 processes are going to be independent from each other as well. And they're each individually squared Bessel processes with particular parameters depending on the distributions of, in this case, the immigration, and also this is the variance of the same type offsprings. Okay, so in this case, this is just Weyl-Winitsky's result, but in more dimensions. Basically, this is all of them behave as if they were independent. They're not necessarily independent, again, so the immigration there can be dependence through the immigration between these processes, but in the limit this disappears. Okay, the more interesting behavior, perhaps, is the following. So here we have that this is the case when the matrix was the top 2x2 top left submatrix was the identity, but there was some positive elements in the bottom row. So which meant that first or second type individuals can produce type 3 offspring. So the number of individuals, the first or second in the population, can influence the number of 3 type individuals in the population. In this case, we have that the first 2 still behave as if independent square Bessel processes, but the third coordinate, we need to normalize with n squared. So as seen before in the Foster-Knight result, the powers of n which were necessary for normalization increased. Here as well, we have this higher power, and then the limit process turns out to be the integral of a linear combination of the first 2 processes. So we have these square Bessel processes, we add them together, and then we integrate to get the third coordinate process. And actually, this behavior is going to be characteristic, so it's going to appear again and again and again. In the next case, we had that. So the first coordinate here behaves like a single type process. We have a squared Bessel process in the limit. The second and third are both going to be integral processes of this first coordinate process with different coefficients. So actually, these coordinate processes are just multiples of each other, turns out. Here we have that this is the case where you can see the matrix described here, but I didn't have space to actually write it. This is the case when type 1 individuals can have both type 2 or type 3 offspring, but type 2 can't have type 3 offspring, and type 3 can't have type 2 offspring. Okay, so this is the case that type 1 population can influence the size of the other types, the population of the other types. Okay, and then the next result Sorry. The next result, this is the same kind of result, but it's somewhat different phenomenon here. So we have that the correct normalizations are 1 over n, 1 over n squared, and 1 over n cubed. And here, it's described here, but I'll just describe it as the relation between the populations now. So in this case, type 1 individuals can have type 2 type offsprings, and type 2 individuals can have type 3 offsprings. So the first population can influence the size of the second type population, and the type 2 population can influence the size of the third type population. And then we have that the first type is just going to be, it's always going to be a squared Bessel process, independent, not with the edger, but so it's squared Bessel process. The second coordinate process of the limit is an integral of the first coordinate process, and then the third coordinate process is an integral of the second. So actually, it's a double integral of the first coordinate process with the particle coefficients. These coefficients here, so this A21 is the expected number of type 2 individuals that a type 1 individual will have. Similar to A32 is the expected number of type 3 individuals that a type 2 individual, the expected number of type 3 offspring that a type 2 individual will produce. So heuristic, this might be expected, as we will see in later arguments as well, or description. So in particular, we have this sort of integral roles are correct. So in the second case, we had that the third coordinate process in the limit of the limit is the integral of the linear combination of the first two. In this third case, the second and third are also both integrals of the first coordinate. And the fourth case, the second is the integral of the first coordinate. The third is integral of the second. So it's an integral, it's a double integral of the first. That's yes, these are the main results. Now I'm going to talk about the proofs a little bit. Maybe not so little, we'll see. So the central part of our proof technique, this is actually, our technique is very different from the one that Vey and Vinitsky used. They use generating functions, but we use, we'll see a different technique. So we define these martingale differences. It's just difference of x from its conditional expectation. Fk is just a natural filtration generated by the process. And with this, we can describe xk. This is similar to how we described the expectation of the process. If you recall, that was the same type of sum, except we don't have this m here. So we just had the b. That was the expected value of the process at time k. But we can get the exact process if we just add together this m, j plus b, and then sum them together like this. Okay, so with this, so this holds in general, not just in our three-type case, for all matrices A. In particular, when if A looks like the one that we considered, so it's triangular with the diagonal being all 1, then we can see what the actual what powers of A look like, and then get these decomposition of the process. So this x, these are different sums, which are going to be more convenient for us to work with. And in particular, so x, k, let's say k1, 2, just looks like we add together the mj1 plus b1 terms. So this is the first coordinate of these martingale differences. And we multiply them by k minus j choose 2, the binomial coefficients, and then add them together. What's nice here is that we can describe the coordinates of x like this, and in each of these, only a single type of m appears, which will allow us, in all these cases, to describe these lower, so some of these coordinates as functionals of other coordinate processes, as we will see. So this is a very the essential with description we use, a decomposition. The rough structure looks like this. In all these cases, we identify which of the coordinates separately will converge to a squared Bessel process. As you can see, that the first always does. Sometimes all of them do. Sometimes the first and second do. We show this convergence for these particular coordinates jointly to the independent squared Bessel processes that we expect. We express the remaining coordinates, which was in the second case, this is just the third coordinate. In the third case, this was the second and third coordinate. And in the fourth case, this was also the second and third coordinate once again, as functions of the first coordinate process. And also some error term, which we will handle separately. But this description of the function of the first coordinate process will be our leading term, which we can show converges exactly where we want it to converge, jointly with the previous coordinates. And then the remaining term disappears in the limit. That's relatively straightforward. So particularly for the case of, the second case, I think this is maybe the best mix of these techniques, which will illustrate the process. So in this case, we had that the first two are going to be the coordinates which converge to square Bessel process. These xt1, xt2, these are just independent square Bessel processes with appropriate parameters. We show this using the previously described decomposition. We actually don't show it directly, but details don't matter too much. We use this particular theorem to do it. So this is a theorem that describes convergence to a diffusion process with these particular functions defined in the stochastic differential equation. This is due to Ispány and Pap. So with some conditions, so we have these u variables here, which have finite second moment, and they're adapted to this particular filtration. And this stochastic differential equation has in an appropriate sense, has a solution, so it can be solved. Then we build this, say, cursive u process from sums of these u variables here. You can recognize that in our case, we wanted to describe the process particularly as sums. So we use these m plus b type variables here as in place of u. And then we got them summed together, and then we could describe the process. We could write the process in terms of these. If we have this here, so we have this cursive u, then this cursive u will convert weakly to u. The u is this is the solution of this differential equation. If these conditions are satisfied, this is basically the condition on the expected value of these u's or on the cursive u that behave as they should. This is a condition on the variances of these u variables, which in our case, again, was these m plus b variables. And this is a Lindeberg type condition on these u's, once again. Okay, so we check each of these conditions. Some of these are simple because the m's in our case are martingale differences. So in particular, this is always 0. And then our beta is going to be 0 in the particular application of this theorem. Yes. And then once we have that, what we do then is that we look at the leading terms of the remaining processes. In this case, this is once again case 2. So the first two converge to square Bessel processes, and then is the third coordinate we're going to be interested in. It turns out that these two are going to be the leading terms. These are, once again, we call that these. So these are just the first ones here. So 1 and 2, I1 or 2. This is this binomial coefficient sum. It turns out that this is exactly equal to this integral of the first or second processes. This sort of rewriting this sum is what we use in in the fourth case as well. That's just it's going to be a double integral. So this turns out that this is a well-behaved function of the processes, in the sense that we can use the following result. We need to introduce this local uniform convergence. This just means that these functions fn converge to f locally uniformly if on each compact interval they converge uniformly, basically. It turns out that there's this is a consequence or a version of the continuous mapping theorem. This can be found in the book of Kallenberg. This says that if we have some stochastic processes which converge weakly and they fall into a nice set. In our case, this is just going to be the set of continuous functions. So these are Cadillac processes. In general, they have Cadillac paths. If the limit process has almost surely continuous sample paths, and these phi n and phi mappings are such that they preserve locally uniform convergence towards continuous functions. I abbreviate this a little bit. Then these phi actually preserve this weak convergence of these processes as well. So in particular, in our case, these cursive UNs are going to be these processes here, the first two coordinates. They converge weakly to these processes. We showed that earlier. So we have this convergence. These are squared Bessel processes that have continuous sample paths. And then these leading terms can be described as functions of these first coordinates processes. So this particular mapping is going to be our phi n. And our phi is just going to be the integral. And it can be shown that this holds. This can be shown this. And then we get the convergence of the leading terms as well. And what remains to do is to show that the remaining terms disappear. This is what in the decomposition earlier, we had this extra term there. This is made up of just the mj3 plus b3 time terms. But this can be shown that it disappears. So we just use some estimates on particularly the second moment of these variables and a kind of Slotsky's lemma for stochastic processes with Cadillac trajectories. Particularly, this just says this. So we have some processes, the y's converge weakly to this y, and we have some z and processes which satisfy this. Then the sums convert, so the sums still converge this y. So these z's disappear in the limit. This is actually basically what it's saying is that these z's converge weakly to the constant zero process. And then the sum is just going to be the plus zero process here. This is actually one of just so this is not, there are some more complicated expressions that also imply this, but this was the simplest one in Jakachiriev, one of their books. Okay, so that was my talk. Thank you. I have some additional slides if someone's interested in the limit theorems for the indecomposable case, or we have some earlier results for the case of two-type processes with that's not necessarily strongly critical. Thank you.
Thank you for you, Daniel, for this nice talk. Are there some questions, please?
Daniel, could you please go back to your main result. I forgot the page.
So these are let's say this is the summary of the main result.
Yes, then when the matrix is the identity.
Yes,
then,
this is when the matrix is the identity.
Okay, then the three components limit in the limit are Bessel processes, right?
Yes, these are independent square Bessel processes.
Square Bessel, square Bessel
Yes.
process.
Yes.
And you have a strong version for your limit. You have a functional limit, right?
Yes, this is the functional limit.
Then, if you take any functional of the sequence on the left, any continuous functional for the topology you are working to get the D distribution.
Yes.
If you take a functional of the sequence of stochastic processes on the left, you will make them converge to the functional of the limit on the right.
Yes, that's right. Yes.
For instance, if you take the first passage time of the guy on the left, it will converge to the first passage time of the guy on the right.
That's right. Yes.
For the squared Bessel process, we have closed. I wouldn't say closed form, but we know the distribution of the first passage times.
Mm-hmm. Yes, you show that before the.
Then you can approximate x taken at floor nt over n. You can approximate also the scale process of this guy.
Yes, that's yes. Yes. Right. That's a yes. That's right.
Okay. What is the topology you are working?
This is the score topology. So the J1.
Which one? M1, the G1.
J1. Yes.
J1. Why did you choose J1?
To me, that was the one I was most familiar with, and also so there was some. We used the same. Let me just skip there. So we use this result, which was also used to prove the indecomposable case result from Ispány and Pap and Galton and Pap. They also used this J1 topology here. We decided to keep that. That seemed to be convenient, but I'm not sure if weaker or stronger topologies would also work. That's an interesting question. If it can be extended to different ones.
But you also used the last result from Jacob-Chirev, which is a kind of Slutsky theorem.
Yes.
Okay. If you remember well, okay, I'm not sure. Okay, thank you.
Thank you.
Other questions, please?
Yep, possibly I have some question.
Yes.
So when you mention your matrix A and the trichotomy related to the radius, to the spectral radius, is it the case later that the speed of convergence is dictated by the second largest eigenvalue or not? Or do you need to transform it into a Perron-Frobenius matrix?
So here, in our case, all the eigenvalues are 1, as you can see. It's possible that in general this would be different. So it's possible that the second largest eigenvalue might influence the speed of convergence. The Foster and A case, they also assume that all of the submatrices have scatter radius 1, so there is not technically true that the second largest eigenvalue is 1, but a lot of eigenvalues are also 1 there. I'm not sure how changing this would influence the speed of the convergence or maybe even the behavior of the process.
Okay, so but for example, in this case here, so yes, the one with convergence, the one by Ney and someone else.
Professor NA,
Yeah,
yes.
yes. Is it the case that they had some insights on the speed of convergence here, or it was not stated at all?
Uh, I do not believe I do not believe they said something about the speed of convergence. Actually, this is sort of so this was, I wouldn't say the side result. This was one of the results in a larger article, most of which actually dealt with the uh, mm, the process without immigration. So this was the second half
Okay.
or last third. I don't think they specified the speed of convergence.
Okay. So in another word, they just have the first asymptotic terms. They don't have insights on the next asymptotic terms.
It's not, we don't know if, we don't know the answer to that. Yes, we don't know if it does or not.
Okay. And also, easy natural question. So you did type 3. What are the difficulties to go to type 4, with 4 types, 5 types, and so on?
Uh, so we think that we're working on another uh, preprinter article. We think this same technique will work for the general p-type case as long as it's also triangular. But probably if the matrix is not triangular but instead block triangular, that it's more complicated. So the description of uh, let me just uh, so this sort of description here, because this also always holds, but it becomes somewhat more complicated if the matrix is not triangular. Uh, we think that a different method might be more simpler to approach that with, but it will probably work for the p-type case. We need to uh, generalize some of these, so we have some lemmas about measurability of these mappings, and they preserve locally north convergence. We need to generalize this to higher dimensions, but that will probably work out.
Okay. And if you forget the probabilistic setting and if you see this as a combinatorial process, so if you see it as trees, so the different types will be that you have some trees with nodes of different colors, and for each color you have a distribution of the children which could be of different colors and so on. So this point of view is an equivalent more or less to context-free grammars. So I don't know if you are familiar with this object, context-free grammars.
I'm familiar with this sort of these lineage trees for Galton Watson
Mhm.
processes. Uh, of the description, but I'm not much an expert on that, so
Okay.
I don't know
So
too
I
much.
will, okay, I will try to go on. It's just that you have a finite set of equations saying from this type of tree you can go to this type of trees, and you have some polynomials or power series in the different type of trees. So you have such a system, and then there are some strong theorem like the Drotal-Hollywood theorem, which is saying that if it is strongly connected, then you have some Gaussian behavior and this type of stuff. So it is more for to follow some parameters. And this type of theorems, they were done also when it is not strongly connected. So which was some of your assumptions later. And then well, there are also some results. Uh, but what was not done, as far as I know, is to see this type of context-free grammars as a process, and then what is the limit process, the kind of Brownian process at the end. And what you are doing for type 3 and so on is a partial answer to this. So it could be quite interesting to have the notion, what is the limiting object between context-free grammars, whatever the spectral radius is and so on. So there
Mm.
are also some cases of equations where you have infinite set of equations, and here also some results, partial results, but the full stuff is not known. So it's kind of echo in combinatorics of your work.
Yeah, it's interesting. I assume that these are strongly connected. That basically corresponds to this matrix being indecomposable.
Yeah.
Uh, yeah, yeah, that's interesting. I know that I saw some talks about limits of trees Galton Watson trees that were very interesting, but I haven't dealt with them yet. But that's definitely maybe something I should look up if there's actually these Gaussian type results, as you said, that may help describe this
Mhm.
somewhat.
But all those models, I did not see them with immigration. So
Mhm.
this is why I was asking exactly what was the role of immigration, because I am not sure in which way it will perturbate, enrich, or is it kind of more or less for free in the other models? This I did not digest fully yet.
I think, well, without immigration, usually these types of results you need to condition on non-extinction. I think that's usually done, or you'd consider like sequences of processes with larger and larger starting population numbers.
Mhm.
So I assume something like that is done in that context as well. But I think immigration can be seen here as just starting another smaller tree from one, but I'm not sure how that fits into that sort of description. Uh, you need to consider. I assume that there's just a singular tree in that model you're talking about.
Yeah, well, it could be also different types,
Uh,
but yes. So I have the impression indeed that immigration is just a possible way to shift the mean so that you don't have extension, and but that you
in,
can.
in one way, yes. So
Mm,
if you have immigration, then you can don't have to worry about extinction.
mm, mhm. Okay, thank you.
Thank you.
Thank you. Other questions? Uh, I have three general questions. The first question
Yes.
is the epsilon process, the process of immigration.
Hmm.
In your model, we have immigration, so epsilon takes values in R plus.
In
Uh,
Z plus, so these are
Z
integer.
plus, okay, Z
Yes.
plus. Can this epsilon be in Z, all Z? That is, we can have some elements entering the system and others leave it.
Yes, that is. So there have been some result examination of these results, where there's not just immigration but also emigration. I think that's more complicated than we wanted to deal with. You need to look at so you need to so some number of people can leave, but then you can't more can't leave than there are. So you need to take these minimums with zero, and then the
Mm.
process becomes sort of bounded in a particular sense. But we don't have results on that. That's
Oh,
probably a very different sort of behavior.
okay, okay. The second question, we can consider your Galton Watson process in continuous time uh, by assuming that each individual, after an exponentially distributed lifetime, gives birth a certain number of offspring. Okay, can us use your results to obtain similar results in continuous time?
I know that you can embed these sort of models in continuous time, like you described. Uh, I'm not sure if these results can directly be used there. I think
Okay,
I'm not sure. I don't want
okay,
to say something
okay.
silly.
The last question, as usual, the polio errors are very connected to Galton Watson process.
That's right.
Are there in your model some polio errors which interact together? Okay,
Uh, so
we
go
have
go
we
on.
have p kinds in your population, and the
Yes.
p kinds are the p colors are the p errors
Yes.
which can interact together. Can I use your results to obtain some nice results about the interacting polyurines?
It's a good question. Uh, I think I think that's plausible. Maybe if you had several urns where there was strictly one-way interaction, so one of them added extra. both the other or something. That seems like it could maybe be something like with the matrix, something like this. But I think it's plausible for some results, but based on the talk the week before last, that was a very different kind of question was considered. I think maybe it's possible that those, so combining the two could be possible, but I don't know how. I haven't dealt with those earned models very deeply.
Okay, and in this slide, in your result, if we change the last one in the diagonal by 0.
So the last one is going to be replaced by 0.
Yes.
Yes.
What kind of speed of convergence we obtain?
Well, in that case, we have that the third coordinate is going to be in each time period. So let's say maybe I don't want to write here. So the xk3 is always going to be equal to the 3 type offspring of xk minus 1, 1 and xk minus 1, 2. Because if this is 0, then type 3 individuals don't create type 3 individuals.
Yes, yes.
So I would assume, or maybe so heuristically, I would guess that this would behave just, so I guess that the appropriate normalization will be 1 over n.
Yes, not
and
1
then
over.
This would just be the same processes as in the first two, because they create some random number of elements. So let's say a random coefficient times itself is going to be the new the value of this coordinate. If these variables are sufficiently well behaved, then maybe you would just need to look at see the convergence here and then choose the larger one, put it here. But we haven't looked at that explicitly, yes. But that is an interesting question that might be that would be worth looking at. I will guess that. So I will guess that this one here adds the extra power of n. So if you remove it, then this will decrease by 1. So I think like say in this case, if type 3 can't have type 3 individuals can't have type 3 offsprings, then I would guess that the correct normalization would be 1 over n here as well. But the limit process would be different.
Okay, please, can you go to the
previous one?
No, to the to this no, the diagonal, the result.
This one.
No, after.
This is the diagonal result.
Main result. The slide of main result.
So here, okay.
Yes. If we change the last one by 0, we cannot have a new elements of kind 3. Never. You can never have any element of type 3, no, because we have 0.
But if these are both 0, then we can't ever have. But if these are positive, then the other type of individuals can have type 3 offsprings. But that's the only way type 3 would, and also the immigration would also be there.
Okay, thank you. Are there other questions, please?
One more thing I just want to specify, I forgot to point this out earlier. We actually have different moment conditions here for some of these. So to show this independent square Bessel process limits, we needed the fourth moment.
So these conditions are optimal. We cannot
these are probably, we suspect they are not optimal. We think that this can be done with second finite. In the single type case, it's been done with the second finite moment, not with fourth. But we needed them just for those coordinates which we want to converge to these independent square Bessel processes. So it's, for example, the fourth one, we don't have the fourth moment because this is implied by the Weil-Winitsky result, and the rest we don't need the fourth moment for. Just wanted to not leave that out.
Other questions, please?
Maybe there is a hope to obtain the same limit under the weaker M1 topology. And then you have more flexible functionals. Many functionals are continuous for the M1. It depends. Maybe the main last tool from Jakocherev, if I remember well, it works also for the M1.
Okay, I'm not too, but that is very
then
tempting.
You get an even more general.
Into more general
You
functions.
can strengthen your result.
Yes, that would
just
be
check.
Nice. I'll look into the M2 tuple and see how many of these work there. I'm not sure. I think this was only, well, it's okay. Like, I'm not sure in what topology in particular this works, but probably this might work there. Okay, that's an that's interesting question. Thank you. I'm not ready to comment on that, but it's interesting.
Okay. Thank you.
We have to thank again Daniel for this nice talk, and see you for the next talk. Thank you.
Thank you.